Hi, good morning, and welcome to the ZP Developer Zone. So every Thursday at 8 a.m. London time, we like to do this webinar really for the members of our ZP Developer Zone. So ZP Developer Zone, I'll sort of essentially just jump straight into it, let's say. So every Thursday, as I say, at 8 a.m. London time, we like to do this webinar. We have the ZP Academy. I'm really going to touch upon the ZP Academy this morning because some of the questions are sort of more, not so much application specific, I'd almost say scientifically, you know, they're technical questions, they're scientific questions. And when you've got those, I think sometimes the ZP Academy is a good place to start. We have our webinars. Welcome to the webinar. We have our collaborations. We post jobs. It's probably worth saying that this week, last week we posted a PhD at the University of Warwick, and this week we posted a PhD at the University of Swansea. So I always say to people, look, you know, if you want to weigh into Zimmer and Peacock, doing a PhD with us is not a bad place. We have our ZP Developer Zone, and we have our workshops. So now we are doing a workshop in Spain. There's a biosensors conference being held in Spain in about May, and we will be doing a workshop there. So topics today, we're discussing pH electrodes. I will be talking very fast. I apologise for that. We've got a lot to essentially get through. So we've got pH electrodes, and we've got wire CGMs, wire continuous glucose monitoring, or wire sensors we've got to talk about. Screen printed electrodes. I had some questions about electrolytes and how to use screen printed electrodes. I just want to say hi to Aftab this morning. If you're in India and you have any sort of questions regarding Zimmer and Peacock products, there's a company called Technando, and it's probably definitely worth reaching out to them. As people wanted to ask questions for sensors for measuring heavy metals in water, we'll touch upon that. Somebody else talked to us about sweat sensors, and we'll discuss that. How to build and operate a SPE, a screen printed electrode, and then COVID-19 sensors, GFET versus screen printed electrode. I also wanted to sort of touch upon that this morning as well. So regarding pH electrodes, I'm going to go very quickly because I just want to list out some products. Look, if you're interested in doing the detection of pH and its kind of applications like urine, you want a very solid state product, not glass and not steel and not a 3D structure, but more of a 2D structure, then, and by the way, I've already put all the links below this video. So if you're looking for these products or pages or videos, whatever we show, there will be links below. So if you're interested in doing pH sensing, then start with the hypervalue pH sensors. We do have a very low cost board that I would also recommend. We have calibration solutions, and we have Julie. Essentially, if you get those four elements, you're in really good shape to start doing solid state pH sensing. There's no price on Julie. You'll notice it's actually free. So the pH sensor is the sensor itself. The OEM board is the board for actually, you know, reading the sensor. The calibration solutions are there because then you're not randomly trying your own solutions. You can get some good science done just off our calibration solutions, and you can automatically interpret the data up in Julie. So that's a good place to start with pH sensors. And there's also a video. Again, this page is definitely linked to underneath this video. Now, wire CGM. Everyone loves continuous glucose monitoring. It is a big application. It's, I don't know, possibly a $10 billion like application for biosensing. When people say wire, they're talking about sensors that are similar to wire sensors were invented by a guy called George Wilson in the early 90s. And when people talk about wire sensors, they're sort of imagining these transdermal sensors like Abbott have the Abbott Freestyle, Medtronic have theirs, Dexcom have theirs. So we do have at Zimmer Peacock, we do have an R&D pack for wire sensors. It's available on a web store. You will need the wire sensors, you will need a cable, and you will need a set of electronics. Now here I'm referring to the Anapot. You're going to hear me refer to this Anapot potentiostat about 3 or 4 times today. I mean, Zimmer and Peacock, with one thing we are consistent. It always is electrochemical sensing. You will need calibration solutions. And again, you can interpret the data through Julie. So Julie is free. So there's a consistency here. With pH sensing, you need the pH sensor, you need the electronics, you need the calibration solution, and you need Julie. Oh, I just want to say hi to Ali this morning. Hi Ali, how are you? I haven't It's good to see you. Now I'm just talking about wire CGMs. Again, you need the sensor. This time you need a cable. You need the potentiostat. You need the calibration solutions. And again, you need Julie. And Julie's free. Hey, Ali, it's worth taking another look at Julie. She's the product, which is still free, has really come along a lot. Now, I'm going to change. So I've talked about pH sensing just very quickly. I've talked really about the things that to get you going. I've also talked about glucose sensing and just the things that you need to get going. Now I'm going to talk about, I had a question coming. It was a little confusing, but the question was, do screen printed electrodes have electrolytes? And so this is a screen printed electrode. Onto it, you would put the sample. So that sample is, what's interesting about screen printed electrodes in the use of sensing or biosensing is there is no solvent. It's actually the sample that's the electrolyte. So here, the blood is essentially the liquid and the salts within the blood are the electrolytes. So when you ask the question in a screen printed electrode, what is the electrolyte? The answer is the sample is actually the liquid phase and the salts within the sample is the electrolyte. And that makes it sort of unusual. See, like a pressure sensor or a temperature sensor or a gyroscope type sensor, those sensors are not in intimate contact with the sample. But when you use screen printed electrode as a basis for a sensor, the screen printed electrode is in intimate contact with the sample. So the answer to the question is, what's the electrolyte used in screen printed electrodes? It's the sample. So here I show the chili sensor, and here the when we literally it's the chili sauce that is the, I want to say, solvent or liquid phase, and it's the salts that are actually the electrolyte in there. And it would be the same, if it's blood, the blood is essentially the solvent or the liquid phase, the salts are the electrolyte. If it's urine, urine is mostly actually water, but it's the salts in the urine that are the electrolyte. Saliva, it's the salts within saliva that are the electrolyte. So what's different when you're thinking about screen printed electrodes and biosensing is it's often the sample that brings the electrolytes. That's why whenever you use a let's say a glucose sensor for measuring glucose, you have to calibrate it for each different type of solution that you actually want to use it in. If you want to use a glucose solution in urine, you have to calibrate it for urine. If you want to use a glucose sensor in blood, you have to calibrate it for blood. If you want to use a COVID-19 sensor on the breath, you have to calibrate it for the breath. If you want to use a COVID-19 sensor in nasal swab, you have to calibrate it for nasal swab. It's a class of sensors that's quite unlike every other type of sensor out there, that the sensor is in intimate contact with the sample itself. I know Ali in particular is interested in water, therefore he really has to calibrate these sensors in that sample type. We were asked the question, well, how do I use a screen printed electrode? I mean, I do have a video here, and all the videos are absolutely linked under the, are linked to underneath this video. But in here, we have a potentiostat, we have a screen printed electrode. You put a drop of, in this case, ferricyanide on there. You run the software, and you should get a CV like that. Electrochemistry to get going is actually really fast. It's, I'm not going to say it's an easy science, but it is an easy science at least to get going and get your first kind of data off it. So that video is definitely linked. Now, the reason I brought up the ZP Academy is these two courses, Introduction to Biosensors and Electrochemical Techniques for Biosensor Developments, these are free. So a few of the questions I feel today are more actually fundamental. And in that case, a sort of a 30-minute webinar on a Thursday morning from us is not going to cover it. But actually, have a look at those free modules. And there are, we call it the knowledge base, educational videos. There's a lot of 50-minute, 1 hour videos that you really need to kind of churn through in order to kind of, it's essentially free education. It'll bring you up to speed, let's say. We did get another question this week. I think this is kind of interesting and relevant to people like Ali, that it's actually looking at heavy metal detection in water. I think this is actually quite straightforward. The technique that you can use for heavy metal or making sensors for heavy metals is you'll need screen printed electrodes, and you'll need a technique, probably anodic stripping voltammetry. This is one way of doing it. You can use ion selective electrodes. I'm actually not going to cover that today, but anodic stripping voltammetry is an easy way to get going. You will use a waveform that looks like this. Part A of this is what we call the cleaning step. We are basically applying a positive voltage. We're kind of cleaning all the rubbish off the sensor, and then we go to what's called a negative voltage, where we're doing essentially electroplating. This is, if you were trying to do lead detection, essentially you're applying a negative voltage, so you're reducing the lead ions to lead metal and you're coating the surface. Then you have an equilibrium step, you just let everything settle down, and then you go this is where the word anodic stripping voltammetry comes from, because you go from a negative voltage to a positive voltage, so from a cathodic voltage to an anodic voltage, and that's the stripping step, they call it. Now, I've mentioned Anapot already today. The Anapot has a scripting language in it, because essentially there I was describing approximately 5 steps. You had cleaning, plating, equilibrium, anodic stripping. So that was 4 steps. So you have to write that as a series of experiments, and you can do that in the Anapot software. It has what's called a scripting language. If you want to do heavy metal detection, to get going is not that hard. You can use gold or carbon. I'll talk. So there's a gold electrode. It's really not that expensive. There's a carbon electrode. It's definitely not expensive. The connector you'll need is a 7mm connector. I will link. Make sure you get the 7mm connector. And this is what the kind of data will look like. I think this data is probably lead and copper. I think it's the lead out here and it's the copper here. So you'll kind of get data that looks like that. And we gathered that data on the hypervalue screen printed electrode. You'll hear me say that a lot. Hypervalue carbon screen printed electrode works. And it's a nice low cost solution. You need the Anapots, you'll need that 7mm connector. Now we got another inquiry this week, and I know I'm talking fast this morning because I'm conscious that there's a lot of questions to get through, and I'm conscious of time. So we got an inquiry about sweat sensing. So at ZP, we have made these sensors that essentially fit on the surface of the skin. I have again linked to this below this webinar video. They're essentially screen printed electrodes where, in the microfluidics collect the sweat, they conduit or they bring the sweat onto the surface of the sensor, and you can do analysis, let's say, on the skin. Now the inquirer sent me a paper and said, I essentially want to repeat this paper, or maybe I want to get inspired by this paper. So one thing I noticed about this paper is it's really dealing with immunosensors. So if I can give any advice, especially if you're doing like a project at university, you want to take on a project that you can do, with the resources that you have. So doing immunosensors on skin and saying I'm going to do the whole thing on skin, and at the end of 3 months or 6 months it's all going to work, that's a really big ask. But what I see here is actually what you're trying to do is immunosensors. So I'd almost say work on the immunosensor part, get that working, and then you can write at the end of your thesis or project future work to do it on the skin, because you really will run out of time if you try to do all of this on sweat on the skin and you're one person. I mean, to do work like this, we will have quite large teams on our plate. So the inquirer wanted to do sweat sensing. When I looked into it, they were really trying to do immunosensors. So let's talk about immunosensors. So there was a video last week, I believe, on this. I've got the link here. I've got the link underneath the video. Watch that because it's a lot more detailed about immunosensors. I talk about gold immunosensors there and carbon-based immunosensors. I'm going to just very quickly touch upon carbon. The reason I want to touch upon it is because it's that hypervalue screen printed carbon electrode again. So there's a good paper out there. I think it's fairly good. I'm one of the authors on it. Sindra, one of our guys, is also an author on it. It's a kind of good paper to follow in some ways. I think it's quite straightforward. You take the carbon electrodes. This is in the video last week. I'm going to go through it very quickly. Take the carbon electrodes. You can characterize it, make sure the electrode's good. If you get it from Zimmer and Peacock, you're fine. You use a coupling molecule based on pyrene. That will stick essentially these coupling groups onto the surface of the electrodes. and then you combine the antibody to that, and then you block off the surface of the electrode with BSA, bovine serum albumin, and we follow each step of that by cyclic voltammetry. Watch the video from last week, I'll go through it slower and in more detail. In testing, we actually like to, in this paper we use differential pulse voltammetry. I will say in a slide, differential pulse voltammetry is good, square wave voltammetry is good, EIS is our favorite system these days. So every time we get a blocking, the signal essentially changes. So when you ask me the question, I want to make a sweat sensor, and then you send me the paper tells me that the first stage is you need to make an immunosensor. So make an immunosensor, and then if you've got time in the project, you can go on to start talking about sweat sensing. But in a sort of undergraduate project or master's project, really, it's enough to make the sensor, and you can just put future work, convert to a wearable sensor. It's good to do what you can do in the time that you're given and the resources that you're given. So to do this work, you need that Anapot. I've mentioned Anapot already. You'll need the 7mm connector. I mentioned the 7mm connector already. And the hypervalue carbon electrodes, I've mentioned those already. So we do like square wave voltammetry to do immunosensors. We do like differential pulse voltammetry. We do like impedance spectroscopy. And I actually prefer these days, if you're making immunosensors, to actually use EIS. The only thing about EIS is the instrument, unfortunately, is about twice as much as the non-EIS instrument. So that's why I sort of say Anapot is good for most, 90% of what I've talked about today. But if you really want to do EIS, then you'll have to use the Anapot EIS. I did get asked a question this week, how to manufacture a screen printed electrode. So I'll just talk about it very quickly. I mean, this is an image, that essentially shows an exploded view of a screen printed electrode. So it shows you the substrate, then it shows you that they've done in this case, probably a silver print. In this case, then they've done another print, which is probably carbon. Then they've probably done another print, which is potentially either silver or silver chloride. And then they've done what we call the dielectric over the top. That's the insulator. So it's a series of prints. The most basic screen printer looks like this. So when I was about 8 years old, I used to do this kind of screen printing, where you essentially have the substrate. In this case, it was the T-shirt. You have a screen with a mask on it. So here's a sort of, essentially, this screen is fully blocked apart from the image. You have a squeegee, which you pull across the screen, literally by brute force, and it pushes ink through the screen and leaves you with the image. Now, obviously, we do this on highly automated, equipment that weighs 3/4 of a ton, or 750 kilograms. But when I first started doing this kind of work, like I say, I was 8 years old. This is really the way I would, this is exactly the way I would have done it. But the reason it's not enough to just manufacture screen printed electrodes. You have to manufacture it, and then you have to do OQC, outgoing quality control. For us, we have Julie, which basically automates all our data analysis. And when we've done that, we can then essentially yield it, because everything you manufacture might not be perfect. So you have to be able to distinguish between what's excellent and what's not excellent. When you've yielded it, you can package it and then you can ship it. So it's not enough to just say, I want to manufacture screen printed electrodes. At ZP, we're ISO 13485, which means we have to follow quality systems in order to make these medical grade products, and basically testing and verification is really important to us. We have generally 2 levels of verification. We have visual inspection, essentially grab an image, put the image through Julie, which we do in an automated way, spot the screen printed electrodes that are good, spot the ones that are bad, reject the ones that are bad, don't ship them. So a lot of people could do visual inspection. We do something else, which is electrochemical characterization of the screen printed electrodes. So again, Julie allows us to It's very industrial scale. We are actually able to test a lot of screen printed electrodes in parallel. We upload the data to Julie. Julie does the statistical analysis and allows us to accept or reject batches of screen printed electrodes. And if the electrodes become a biosensor, it allows us to analyze and reject biosensors. In this case, I'm looking at a G2 glucose sensor. We do functional testing, and that means that we could, if you're trying to make a screen printed electrode that's going to be used by amperometry, we'll do amperometric detection on it. If you're trying to make a screen printed electrode that's going to be using ions, then we might analyze it by open circuit potential. If you're doing an electrode that's using voltammetry, then we might do voltammetry analysis of it. And what we do is we go along the product line or production line, testing electrodes, and essentially doing something that we call wafer mapping, so that we know the performance, and we color coded it here so that we know the performance of electrodes. And what we can actually do is actually take that electrochemical performance and tie it to the electrode of interest, so that if you do have, let's say, across a manufacturing line, if there's variation, you can either just reject it because of the variation, or you can actually understand that's part of the process. I don't want to throw away too many products. And so as long as you understand that variation, you can actually QR code it and use that variation in your product. So for example, if you were making a water sensor, you would ship the sensor out there with a QR code. The end user would read the QR code, which would then tell the software, this is the sensitivity, this is the offset. So then when they use that sensor, you would account for the individual sensitivity and offset of that screen printed electrode. Right. Finally, we got an inquiry this week for somebody who's looking for a GFET COVID-19 electrode. And all I say on that is GFET, graphene field effect transistors, are very expensive. I would actually take a look at maybe using a graphene screen printed electrode. I definitely have put the link to this underneath this video, so hopefully I have, and I'll just check. But yeah, there's a graphene screen printed electrode from ZP. If you're interested in GFET, this really doesn't matter whether you use a graphene electrochemical sensor or use a graphene field effect transistor. I like what Ali said. He said, you've passed a huge amount of information in such a short time. Yeah, Ali, I know, I feel it, man. Thank you for the support. So you're very welcome to look at GFETs. I always admire people for doing that. Also take a look at the alternatives. I mean, the reason I say that is we're able to manufacture the screen printed graphene electrodes much lower cost. I did a whole speak on immunosensors earlier on. If you're interested in making a GFET COVID-19 sensor, back up slightly and say, actually look at the graphene screen printed electrodes, and then look at the videos I referred to earlier on about how to make immunosensors. And if you combine graphene with immunosensing technology, then you're on your way to a COVID-19 sensor. We would do it as a at Zimmer Peacock, we kind of essentially have 6 steps to get from idea to full manufacturing scale, and we would call that a proof of principle. So because AFTAB's online this morning, AFTAB, in this case ZP, would do this kind of work as a proof of principle study. Right. So thanks, Ali, for the support. I appreciate the comment. So today, pH electrodes, honestly, I really quite like screen printed pH electrodes. They're solid state, they're low cost, go for it. Why a CGM? It's a big market. It's a $10 billion market at the moment. ZP has essentially a starter kit on that. I listed out. You need the sensors themselves, the cable, the anapot, the calibration solutions, and Julian, you should be good to go. Screen printed electrodes, how to use them. There is a video about ferricyanide. I have linked to that. Sensors for heavy metal detection. It is a favorite of mine. Hyper-value screen printed electrodes absolutely work. I do show the data above. Sweat sensors, break that problem up. Don't go straight for sweat sensing. Say, my overall goal is sweat sensing. The first thing I'm going to do on my project is immunosensing. And how to build and operate a screen printed electrode. It seems quite simple to do. you can do it on almost on that wooden rig that I showed. I did, I did it myself when I was young, but that's not the way we do it. We do it highly automated. COVID-19. Take a look at graphene screen printed electrodes, and take a look at those immunosensor videos that I said above. Right, it's 8:25. It's going to be 8:26 in a few seconds. So I do want to say thank you very much to Ali. It's nice to see you this morning. Thanks to Aftab. I appreciate it, guys. I'm literally going to stop this video, jump in a car, and go to our Swansea office this morning. So thank you very much, guys. It's nice to see you again, Ali and Aftab. Man, I'll talk to you very soon, and take care.